Now, you all know what GPS is, right? What does that stand for? Global Positioning System. How about GIS? If you've read ahead, you might know that it stands for, actually it can stand for a couple of things. In the old days, when it was invented, if it was invented, it's kind of hard to say if it was actually invented or not. When it became a thing, that's the way I can put it. When it became a thing in the 1980s, about the time I was becoming a geographer is when GIS became very, very new and was the big thing in geography, and it's still largely the big thing in geography. Geographical Information System is what it means. Geographic Information Systems. And today you see some folks referring to it as Geographical Information Science. Well, that's okay. It's not really a science. It's more of a tool, but it is a tool that allows us to do maybe some science. So GIS, Geographic Information Systems. It's not something that is just for geography anymore, right? Like orange juice. It's not just for breakfast anymore. GIS is not just geography anymore. It's used by just about every social science, natural science, especially in the biological sciences, in geology. In geology, it's even really, really cool because they can do three-dimensional GIS. Anyway, Geographic Information Science or Geographic Information Systems is what we'll talk about. And then finally, remote sensing. Remote sensing. Very general term. It has, for most people, a pretty specific definition and meaning, but it really needs to have a fairly general definition. And so I'll try to tell you what that means. Remote sensing. I sense it out there somewhere. That's what it's about. Remote sensing. For the most part, we're talking about collecting data. And a geographic information system is really not a data collection system as much as a data management system and an analytical platform. So remote sensing is in geography mostly associated with spectral and multispectral imaging of the Earth's surface. Imaging of the Earth's surface. My father was actually engaged in remote sensing in his career, but they never called it remote sensing, and it wasn't visual. His career was engaged with sensing objects using sound waves. And I won't discuss it any more than that, but you can sense objects in many different ways. Okay, you can sense things with sound waves and the way that bats operate, with echolocation. If you go to the hospital, and probably a lot of you, some of your athletes, you probably had, other than X-rays, like all of us have had X-rays, you've probably had, what we call it, sonograms, or what are the various terms for where you can actually look at tissue in your joints or something, and to make sure that it's all there, not all torn up. So there are a lot of different ways to sense. In the medical fields, there are all sorts of ways of imaging and sensing tissues and getting ideas of what's in there. Okay, so remote sensing in geography is mostly about doing that same thing, but on a different scale, looking at the surface of the Earth, looking at plant communities, looking at maybe how built up a city is, so that you can get an idea of how much surface runoff is going to occur downstream. all sorts of reasons that you would want to understand and identify different types of surfaces. In remote sensing today, we use both satellite remotely sensed data, from satellites that are 12,000 miles above the surface of the Earth, to satellites that are only a couple hundred miles above the surface of the Earth, and also airplanes that fly various levels, even airplanes that only fly maybe a few hundred feet above the surface of the Earth. And now, of course, drones that fly really close to the surface, very slowly, and allow you to sense a surface, to read a surface and basically take a picture, but a very sophisticated type of picture, of the surface of the Earth in a very high resolution. So the technology has done this. The technology started off with aerial photos. Who started doing the first aerial photography? Well, they didn't even use photography, because the first aerial surveys were done by hot air balloons, and people would sketch what they saw. Later on, photography, they would go up in hot air balloons and take photographs. During World War I, you have the first airborne photography. Okay? And then during World War II, it really got sophisticated, where airborne photography became standardized, and even before World War II became fairly standardized, so that we had really good aerial photography. Most of the topographic maps that you will ever find in the United States are based on, at least the newer ones, are based on aerial photographs. Then by the 1950s and 60s, we began to get satellites up in orbit, and we get the first weather satellites, and the very first satellites that in the 1970s that were able to record the surface of the Earth. Not in very good resolution, but we could see things that we had never seen before because of satellite imagery. And ever since, satellite imagery has gotten better and better, until finally the imagery that we're looking for now is not even done by a satellite. It's done by a little UAV, a little drone flying around with a camera at very low altitudes. So the technology has really matured. And all the time, what we're doing is basically bouncing light waves or sound waves or other types of radiation off of the surface in order to record what that surface can tell us. In some cases, magnetic field can tell us more than what the surface can tell us. All right, the GPS, Global Positioning System, is a system that got started mostly during the Cold War and evolved after the 1990s for the most part into what we have today. And your cell phones, of course, are not necessarily using GPS the way that we understand GPS, what I'm going to explain it to you, is they're using the cell phone network to do basically the same thing. And then we have GIS. So let's talk about each one of these a little bit. Remote sensing data, again, just involves imagery based on generalized values within a grid. That's the important thing here. Most all remote sensing, if not everything these days, is based on the existence of a grid, a set of pixels, no different than your digital photo that you took this morning on your way to class. Right? And so if you have a smartphone and you took a digital photo, you know that digital photo, whether it's 8 megapixels or 24 megapixels or something insane like 56 megapixels, on a medium format camera, huge amounts of data. Each one of those photographs simply has a little square with a different color, a different VGA color. And that VGA color is defined by a number, right? So essentially, anything that we are talking about in terms of a remotely sensed data set is more or less a digital photo of some sort. And all of those digital photos have these standard squares, gridded squares, pixels, or rasters, in fact. We'll call them rasters because that's the formal term. And those rasters are representative of reality. They're not reality, but they're representative of reality. And they have a quantitative reading, a quantitative statement. Maybe that statement or that number indicates a color or a shade of a color. And that's all. Together, the mosaic of all of those millions of pixels or rasters tell us much more. So, remotely sensed data, basically digital photos, digital pictures composed of regular pixels, regular rasters, and they come off of all sorts of different types of sensing devices. All types of sensing devices. That's remote sensing. Just some visuals here to show how it works. Something like a Landsat satellite is constantly perusing the Earth's surface, recording data. This is actually from Oklahoma. Anybody have any idea what county or what part of Oklahoma this may be from? This is one of my favorite counties in Oklahoma. Of course, I have 77 favorite counties in Oklahoma. So where would this be? What do you see? If you're nearsighted like me, you might need some glasses to see it really well. You see farmland. How do you know that? Are you looking at something that you would see from an airplane? Would it look like that? No, right? It wouldn't look like that. What you're looking at is a false color image, where everything that you see that is red is actually green. Okay? It's intentional so that you can see where all the red, i.e. chlorophyll, green is. You can also see some green, but I'm not sure exactly why you see some green and some red. But it's probably one particular crop. My guess is it's like sorghum or wheat or something, or maybe corn. But you can see these. You see these perfect little circles? Those little circles are center pivot irrigation fields. And this is from Texas County, Oklahoma, the county in the middle of the Oklahoma Panhandle. Texas County is a county that is the most agriculturally proficient, most agriculturally lucrative county in the state of Oklahoma. And they grow more corn in Texas County than any other part of the state of Oklahoma. It's totally bizarre because 100 years ago, they didn't grow any corn in Texas County at all. It's all based on irrigation. So this particular satellite photograph or satellite image is intentionally changed so that you can identify certain bandwidths, the certain type of reflectivity of a particular crop. So certain crops have different signatures, what they call digital signatures of their reflectivity at a different time. A lot of our aerial photography that you use today are a lot of the digital imagery that you use through Google Maps or something like that is airborne photography. And airborne photography is still around, still very, very good. One of the major users of aerial photography today is one of the major users are municipal governments. Okay? Sorry. city governments and county governments have contracts with companies that do flyovers, and they do very frequent aerial photography surveys of residential areas. And they have software that allows them to identify changes in imagery over time. So, for example, say your folks have a house, and maybe they spend $50,000, $100,000 adding an addition onto their house. Maybe they expand it outward a little bit, just so they can add like 500 square feet to their house. Okay, that would show up in the aerial comparison of the municipal government. And guess what would happen? The tax assessment is going to go up. Okay? So it's worth a lot of money for municipal governments to be able to identify minute changes in things like properties that can be taxed, so that they can charge more accurately taxes to citizens. You might think, I always liked aerial photography until now, right? So they're actually very vigilant about that, and there is money to be made. We can also do other cool stuff like model the surface of a landscape. And here you can see I think this was done with a point cloud software that uses a laser scanner, a digital laser scanner. And the term used these days for this is LiDAR. It's kind of like radar, but with lasers, so it's LiDAR, laser imaging scanning. And a laser imagery creates millions and millions of points that have that are able to sort of see in three-dimensional space. So when the data are all cleaned up, you can create sort of a three-dimensional model of something like this. This is probably no surprise to you. Of course, there's a drone with photography, aerial photography. This is an emphasis here at OSU now, particularly with agriculture, because when you can do large-scale, very close-up analyses of crops and of fields, as fields go through the seasons, and as different climate and weather patterns affect field and crops, as the crops change, we can have a much better idea of how the crop is affected by changes in weather, changes in amounts of rainfall, or how a crop perhaps is being affected by a pest, maybe a disease or an insect invasion. So these are very, very useful in agriculture and as well as many other things today. Here's an example of very small scale stuff that a satellite still really would not be able to pick up. And with a drone and with satellite imagery from drones, you can go out all the time and collect information for specific landowners, specific fields. This is an example of how a remotely sensed image, a raster-based image of reality might look. So keep that in mind. The raster data, each one of these rasters or pixels is merely representative of what the image originally saw. Now, when we talk about geographic information systems, we need to make a comparison between two types of data. And this is something you should pay attention to. In remote sensing, for the most part, you're going to be collecting raster type data. Just pixels, photographs with pixels. And in geographic information systems where we draw maps and we have to draw things to scale very quickly and do calculations with regard to area and length and positions and that sort of thing, it makes a lot more sense to use what we refer to as vector data. Vector data is basically geometric data, okay, along a Cartesian grid of some sort. Here we have an XY axis. Each one of these points within this field has a specific location identity, right? So we can define this point by its relative distance to this point by using an X, Y position, okay? Or what we might call a coordinate. So its coordinate is defined as somewhere along the y-axis and somewhere along the x-axis, but it's right there, just like your position and latitude and longitude on the surface of the Earth. So this type of data, vector data, which is made up of points for the most part, but what happens when you connect 2 points? You get a line, right? 2 points connected are a line, or infinite number of points connected is a line. When you close that line, you create a polygon. So we have an area. So all vector data are based on points, although we can create lines and polygons with them. Vector data, though, are much, much more flexible or manipulatable, is that a word? Much more easier to manipulate and to work with in computing time than raster data. So the lesson here is that a geographic information system's great utility is its ability to marry vector data with raster data. Okay? Its ability to join and to utilize both vector data and raster data. That's what a GIS does. And that's about all it really does, but we've just figured out lots of other things you can do if you can do those 2 things. Remote sensing itself doesn't do much except create a picture. And vector data doesn't really do much at all here unless we have questions to ask and things to measure. So vector data and raster data. A geographic information system is basically a way to take all sorts of different spatial distributions or maps and lay them on top of one another or compare them across one another and do it very, very quickly. And to ask questions about, what in the world, the questions are endless, but if you can see this at all, you can say, okay, well, here are some physical geography attributes or physical geography data, and then here are some human geography data, the survey network versus the hydrography or the drainage areas. And we can begin to ask questions. We can do queries to ask, okay, find all of the city lots that are within the 100-year floodplain along this river. And we can identify those very quickly. So this is a data management tool. And I'm going to see, does anybody have the time? That's 40. Oh, okay. Well, let's cut it off, and we'll come back to the last one, which is GPS, I guess. That's it. All right. We'll see you on Wednesday, and we might catch up. We might not.